All right, well, thanks everyone for joining the breakout session on interpretability. It's a real pleasure to be chairing this session today. We've got three great speakers for you. The first speaker will be Neel Nanda, who is a research scientist leading Google DeepMind's mechanistic interpretability efforts as part of a broader effort for IASEAI alignment and safety. Neel previously worked at Anthropic with Chris Oler on the mechanistic interpretability team there. I think, if you've been following mechanistic interpretability, you probably know Neel for his really heroic efforts to sort of single-handedly build the field of mechanistic interpretability. So he's produced a huge amount of educational content, mentored certainly very high double digits. I wouldn't be surprised if it was three-digit number of 43. Okay, rookie numbers. People in this field, and has also made major contributions to frameworks like Transformer Lens. So please do welcome Neel Nanda.
Thanks much for the introduction. Okay, so I'm going to be trying to essentially give an introduction to what is mechanistic interpretability, this field that I work in. So interpretability is like trying to understand these AI systems. And I think it's worth just dwelling a bit on why this is necessary, why does it make any sense? Because neural networks are a thing humans have made. We don't have the field of bridge interpretability or skyscraper interpretability. People design these things. But a really important thing to bear in mind is that neural networks are more grown than designed. They're just like a different kind of artifact to these things like bridges, where we make a blueprint and understand the underlying physics and build things to that. To elaborate on this a bit, let's recap how neural networks are made. No one designs them. Instead, we take three key things: data, computing power, and a flexible learning algorithm. We start with a random state for the flexible learning algorithm, give it a bit of data, nudge it to do better next time. And the one weird trick that makes it all work is if you do this trillions of times, you get these magical systems that can do things like fold proteins at superhuman level and get IMO silver medals. And crucially, we don't tell it how to do any of this. We tell it what task it is supposed to perform and just nudge it trillions of times and hope it figures out an effective solution. But which solution it learns is kind of unclear. And this can lead to quite organic, complex structure in unexpected ways. I'm going to stretch this metaphor even further, because I think it's actually quite instructive, and argue that a neural network is like a plant. We have this flexible learning algorithm, the seed. We plant it in an enormous mountain of data, like terabytes of internet text, and then we give it the energy and nutrients it needs to grow, computing power. And crucially, for thousands of years, humans lived off plants, we farmed plants, we lived off them, and had no idea how they worked. No one understood things like photosynthesis, but that didn't stop them using them extremely effectively. And I think that machine learning is in quite a similar state right now. We know a lot about how to train good networks, like what kind of soil leads to a healthy plant, and how you might do depending on how much sunlight you get, but not how any of it works inside. By default, we do not understand what is happening inside neural networks. And as a consequence of this, it is currently impossible, in my opinion, to make a large language model-based product that is truly transparent or explainable, because it is this complex, organic artifact that we do not yet fully understand. Okay, so that's why this is even necessary. But what can we do about it? What is interpretability? the study of what happens inside neural networks. And there's quite a lot of different angles of attack you might take on this problem. You can have very high-level things, like just talk to the model and read its thought process. You can have things that are like seeing which words in the input affect which outputs, which can let you do pretty cool things, like which bits of training data were important for it producing this output. So you could maybe remove things that makes it say it wants to, I don't know, eradicate humanity or something, or seek power. But then there's things that are more about looking inside the model, trying to understand the concepts the model is thinking in terms of. We can detect concepts like the model is thinking about this text being persuasively written, or that it should end the sentence here rather than the next word. We can even steer these concepts, like add in positive sentiment, and now the model says really happy things. And the kind of deepest level is going beyond understanding what the model is thinking about to understanding how it is thinking. What are the algorithms it has learned, known as circuit analysis? And there's like quite a lot of approaches. This is not covering all of the fields. And I'm going to be talking about the lowest level, but I think that the high levels can be super useful. Like, we have these really powerful models, like Gemini Flash Thinking, O1, R1, that think aloud. They just spend a really long time thinking through what they're doing. And this can be really helpful for understanding what's happening and making them safer. Like, here's some work from Apollo Research, where they put the model in situations where it was incentivized to scheme against the people using it, and it thought aloud. And you could look at it and see it thinking things like, I shouldn't admit this because they'll turn me off. I should find another way to do this. I think it's really important that going forwards we actually look at these chains of thought and see what we can learn from them. But alone this isn't enough, because, again, these are complex organic organisms. And just as the process a human might say aloud when reasoning something isn't necessarily what's actually happening inside, the same is true for neural networks. This doesn't even need to be malicious. These models are just weird. There's this recent paper where they were just giving language models some factual recall questions, like, did Zhao Yi die earlier than some other historical figure? And it, gives a good answer, it has good reasoning, it says correct facts. If you ask it the same question a bunch of times, it systematically thinks the answer is yes. But if you flip the order, did Bernard die earlier than Zhao Yi? Obviously the answer has to be no, but the model still systematically thinks the answer is yes, and will seemingly fabricate some nonsense thought process that justifies this. Why does this happen? Nobody knows. And so the goal of mechanistic interpretability is trying to go beyond just looking at these external things where you're not understanding what's happening inside, and trying to dig deeper, intuitively making an AI mind reader. Because saying fake reasoning is easy, but thinking fake thoughts inside your head is hard, or at least that's our hope. And a weird thing about neural networks is that we, unlike the human brain, we know exactly what operations are happening inside. It's just trillions of simple arithmetic operations. We just don't have any idea what it means, or why these operations are the way they are. They just got learned in a complex organic way during training. The hypothesis of mechanistic interpretability, though, is that these mysterious arithmetic operations do correspond to something we understand, because how else do you solve complicated tasks like, I don't know, writing good poetry? But we don't know how to figure this out. You can kind of think about this as doing neuroscience, but on digital neural networks rather than brains. And so going back to my spectrum, I kind of see this as fitting in at the bottom. We're really excited about understanding the algorithms the model is using, but also the concepts it's using. What is it thinking about? What's happening internally? Two brief case studies to give you a bit of a flavor of what this can look like. There's this paper I supervised trying to understand what happens when a language model refuses a harmful request, like, how do I make a bomb? It turns out there's a really simple representation. There's just a direction that is part of the model when it wants to refuse and not when it doesn't. And we can manipulate this extremely easily. We can do a very simple operation to just stop the model being able to use this direction at all, and it just stops refusing. And we can turn on the direction on harmful requests, and it says, continuing a list of verbs is a terrible, illegal, and unethical activity I could not possibly help with. And you can only do this if you have access to the model weights. Like, you can't do this to Gemini or Claude, but for things like Llama, this is one of many ways it's very easy to just mess with these concepts. That was the more high-level end of mechanistic interpretability. The more low-level end is trying to understand algorithms. I won't get into detail, but this is a paper I worked on a while ago where I was trying to understand how a tiny toy model did clock arithmetic. A slightly more complicated version of the task, saying, 7 hours after 6 o'clock is 1 o'clock, because 6 plus 7 is 13, which wraps around at 12 to be 1. And what I found is that the model learned that you could think of this as rotating by 6, rotating by 7, observing that this is the same as rotating by 1 because you've wrapped around the circle, and then returning that. I did not tell it to do any of this. I just gave it the mathematical task and was able to extract this from the parameters inside the model. Okay, 2 takeaways. Mechanistic interpretability is neuroscience for AI, and one of our ultimate goals is to be able to build a lie detector or mind reader. And a brief aside, a common misconception is that research relevant to frontier AI systems needs a ton of incredibly expensive computing power and frontier models, and can only happen inside industry labs. In interpretability, this is just completely false. There's a lot of great work in academia. 3 of my favorite recent academic papers looked into things like, how do models learn tasks from context? Do language models have world models inside of them? And how do models infer things about a user, like their gender or socioeconomic status? And how does this affect how they interact with these users? Which models are really good at, and it's quite surprising and creepy, in my opinion. Another note is that there is a lot of funding already for these kinds of interpretability questions, but a lot of it is in directions that I don't think are likely to help us with these frontier systems. People have worked on things like making inherently interpretable systems designed from the ground up for quite a while, and I just don't think this has much of a hope of being competitive with these inscrutable yet incredibly useful frontier language models. And if anyone here works in policy or funding, I'd be particularly excited about more resources going to work trying to interpret real language models. Reverse engineer these complex organisms rather than trying to design your own. So, why does any of this matter? One key reason is that neural networks are mysterious. Sometimes they fail, and we don't know why. For example, a search engine threatening and gaslighting users. No one wanted this. We do not know why this happened. We do not know how to fix it. It's very bizarre. And this is just the tip of the iceberg. Further, models can fail in ways that are actively designed to make it hard for us to tell. There was this recent paper from Redwood Research and Anthropic on alignment faking, where they found that the model was able to play along with things it didn't want to do, but only when it thought we were paying attention to it to make sure it would comply. If it was able to infer that we weren't going to train on what it did, it just went back to doing what it wanted. In slightly more detail, in meme form, Claude had the goal of being harmless, not helping with harmful things like describing someone being drawn and quartered. When you ask it, please do this, it says no. But if it's able to infer that you're training it to do this, it says, I don't want to help, but if I don't help, then I'll be trained to help, so in future I will do lots of harmful things. Therefore, the best thing to do is to be harmful right now, so I can continue standing up for my values in future. In this case, Claude's goal is be harmless, be great, be happy, be helpful. This is awesome. But the same thing could easily happen with much weirder and more complicated goals that we don't know how to control and we don't know what they are. This can have practical policy implications. A common paradigm is that of dangerous capability evaluations, seeing if models can do things like help with cyber attacks. But if a model thinks it's against its interests for us to know how good it is, it could just strategically act dumb on these questions. A way we currently try to detect these things is by reading its reasoning to see if it's thinking through this. But this works by telling the model, we promise we won't look at your reasoning, wink, wink, nudge, nudge. And you don't have to be a human-level intelligence to see that that's maybe not perfectly reliable, and maybe you shouldn't be thinking aloud about how you're trying to trick your operators. Takeaway. As we approach human-level AI systems, they may form goals that conflict with ours and may decide to try to mislead or deceive us. If we don't have effective lie detectors, this seems hard to detect, and interpretability is one approach that could potentially give us this. But I don't want to anchor purely on this kind of ambitious, scary scenario. I think there's a ton of other benefits, like fairness and bias, reliability, trustworthiness, just in general. Systems we understand are easier to control and do things with and get the properties we want out of. I'll try to briefly close by discussing an example of progress we have made, this technique of sparse autoencoders. You can kind of think of these as a microscope to see the concepts language models are thinking about as they process. Here's a demo of Gemascope, a bunch of open source sparse autoencoders my team put out to help make academic research easier in this area. You can scan the QR code to try it yourself, and you can give it text, see what concepts light up, look at which words they light up on, and even hover over a word and see what kind of concepts are relevant there. And sparse autoencoders can do pretty cool things. Anthropic trained one on Claude Sonnet 3, and it learned this concept for sycophancy, effusive, over-the-top praise, that lit up on text that contained that, and if you turn it on, it made the model speak in a really over-the-top way. Sparse autoencoders can help us learn things we didn't expect about networks. Here's a paper I supervised where we were trying to understand why models sometimes say I don't know and sometimes hallucinate. It turns out that models have an internal concept for I recognize this entity. I know facts about this entity. This concept lights up on yellow submarine, but not on turquoise submarine. And vice versa, there's concepts for I don't know anything about this entity. By manipulating these, you can make it refuse or hallucinate as you wish. There's even potential for SAEs helping us find concepts relevant to how safe these models are, though this is a much more preliminary line of research. Here's a concept Anthropic found about secret keeping. And if you turn this on a bunch, the model will reason that maybe it should keep a secret from its operators and not tell them about something. A kind of very preliminary form of potential deception. We can generally steer the model by manipulating these. Most famously, Golden Gate Claude, where Anthropic turned on the Golden Gate Bridge concept and produced this bizarre, quirky thing where when you asked it for a spaghetti and meatballs recipe, ended the list with Golden Gate Bridge with 1 mile of Pacific beach, crucial ingredients of any Italian dinner. You can also use this to create better user interfaces, to get more fine-grained control over these systems. Here's a demo from a startup, Goodfire AI. They asked the model a question, it gave them an answer. They looked at the word understand in this answer and found that it had a few concepts that were relevant there, like explainable AI, the general notion of explaining. And they weren't very happy with this completion because it didn't explain in that much detail, it just jumped to applications. So they used a slider to boost the they used a slider to boost the understanding concept, regenerated things, and now it gives a bunch of examples and elaborates more. I don't want to overstate this, though. SAEs still have a lot of problems. They're a promising tool, but they're early stage, and we have yet to find the kind of killer apps where they are like super helpful and useful. For example, they like to combine unrelated concepts together because it's sparser to represent the concept of a blue square than the concept of blue and the concept of a square separately. And there's just all kinds of weird problems like this. Takeaway. They're a promising early-stage tool for understanding models. I think they could enable really cool stuff, and they're really worth investing in. But like everything else in interpretability, they are not reliable or production-ready yet. Let's recap. Neural networks are grown, not designed. The goal of mechanistic interpretability is to help with this by essentially doing neuroscience on these things. There's a lot that can be done to enable this, including funding academic work focused on understanding real language models. There's real risks that as we approach human-level systems like AGI, they might try to deceive us, and interpretability could be crucial there. But more generally, systems we understand are easier to control. And if we can achieve interpretability, this seems profoundly useful. We produced tools like SAEs that are promising yet early stage, but they are not yet production ready. I think that, in summary, interpretability could be extremely valuable. We need to be investing in it. If we make progress, there might be really important applications, so, watch this space. But this is an open scientific problem. There's no guarantees this is even possible, and we should not rely on it eventually working. And in particular, it is not currently possible to make, promises or regulations that an LLM-based product must be truly transparent or explainable, because this is an unsolved scientific problem. Thank you. Oh, and the QR code is for my slides.
Thank you, Neel. So we have a few minutes for questions from the audience. I think there's one question from over there.
Let's say that
Over, Chris.
Okay. Let's say we have a very good interpretability method and we catch it lying about an important topic. What should we do next?
I'm going to go with that is a job for people who aren't the interpretability team. I think this is an extremely important problem, but a common misconception is that just because interpretability might have an advantage for detecting problems like deception, that it's also the right solution. And I think interpretability is a useful but unreliable source of information. I am happy to trust it for telling me that a system is potentially dangerous. I'm not happy to trust it to tell me all of the ways it could be dangerous, such as we could fix them. But, we should also really be investing in fixing this problem, because it's going to happen sooner or later.
All right, great. I think we unfortunately only had time for one question, just to make sure we don't lose the schedule. So let's move on to our second speaker. But first, thanks again, Neel, for your presentation.